I thought we'll just start instead of making it anything formal. Maybe I'll just thank Ching in some sense for having these seminars and having all these fun people come through. I feel every time I've met folks that he's brought on campus, I learned something new. I guess in this particular slot, it's a bummer that I don't get to meet someone new, but in some way.
Just something new.
Yeah, or I get to, it's always fun to say something and then hear somebody else's reaction to it and how they think about it differently. So I hope in that perspective, I get to hear some of your instantaneous reactions as you go through it. But there's no need. No, I think maybe I'll introduce myself in that way. I think I'm on the 4th floor. Yeah, where I'm just colleagues with Jeff used to be a few doors down from me until he went down to the 3rd floor, but soon he'll come back up to the 4th floor. And I think I've been in Michigan since about 2009. And it's sort of fun to think of, even my own journey as a faculty member or even as a student, how some teams, perhaps I wonder if Laura also thinks of it in that way. Sometimes one learns these things like in 551, like SVD or bases, and you think, wait, at some point, maybe is that done? Or how much more can one squeeze out of it? And then before you know it, something else comes and you're like, oh, wait, that is something I thought wasn't relevant, turns out to be relevant, and then the story keeps going. So this is one of those stories. So one of the ways I want you, if you would, I'll tell you a little bit about it, but I want to also kind of ask you to actively think a little bit what comes in your mind when you think of this word asymmetric SVD, right? So I'll talk to you about what that is, but perhaps before I start, you might just wonder, what exactly is this guy saying when he says asymmetry, and see if you can maybe guess what I might do so that if it's not what you might have guessed, perhaps the surprise of it might be interesting for you, right? But I'll tell you what it's not. It's not a SVD of an asymmetric matrix, right? That's not obviously, that would be too silly to say out loud. Even though sometimes in the beginning one wonders whether, when learning these things in 551, like, wait, what do I do with rectangular other stuff? Okay, so the main goal for this talk is to talk to you about this new asymmetric Eig method that works in a regime where the SVD fails. So the first part of the talk is really giving you a feeling for when the method fails badly. And this failure condition is important only because if it didn't fail, well, there's nothing to solve. So when it fails, there's something to solve. And the initial idea was when we go through this exercise, you'll see that as I change one knob of my simulation, the SVD works, then suddenly it just breaks down. And one might wonder, is there something that redeems it, so to speak? And it turns out this method will redeem it. So for you at some level, while I talk about it, maybe you might wonder, even as I tell you about the method, so to speak, so you might try it out. Perhaps the more fun thing is for you to wonder, how might I and my collaborators have come up with that idea in the first place, right? What was the computational experiment that we might have done that gave us a feeling that maybe this idea could work? And then, of course, the math ends up proving that it does work. Sometimes I feel in papers and all, that's the most fun part, right? Like, how did that person think to do this that the previous person did not, right? So perhaps you might put that hat on and see whether you can guess what might I have done that might given me the belief that this could work. Because after all, in any of these things, it takes so long to do it, to do the actual work, that unless you're reasonably convinced that it's going to work, how do you actually start the work, so to speak? Okay, let's get this guy. Oop, looks like it's working on the Zoom screen, but not on the projector.
Oh, flash.
Yeah, what is going on? I see it on the Zoom. So
maybe turn it off and on.
We can hear this screen.
I think this is sharing from here. Because that is this one, okay. Go off and on all the way.
Shouldn't it raise?
Yeah, because I'm doing Apple TV now and it's not quite. Okay, now let me go to laptop again. Plug it in.
The SVD already is.
Yeah, so you're thinking, which is good. So I'm going to do something very weird to it that is not obvious.
Also, lower zoom.
Yeah, should we do that?
Yeah. So
Oh yeah, okay, we can.
Stable.
Oh, that's not what he means.
And the dimensions.
Yeah, he said that's definitely.
That's not. Okay, good. We kind of double hacked it. I'm doing this on Zoom and then the PC Zoom screen is being shared on that. So it's like a relay in a weird way. Okay, so let me tell you the problem. Maybe you've seen this before, but if you haven't, it's kind of straightforward. There's a low rank matrix, so that's the 551 style decomposition in terms of the SVD factors. R is the rank. We'll typically assume rank is known. And the idea is you don't know what this A is, but you know it's low rank. But what's given to you is this A tilde. And the key point is A tilde is basically A Hadamard product with a mask, or equivalently, A tilde observes this matrix Aij element with probability P, or there's a question mark with probability 1 minus P. Right? So if P is equal to 1, that means you get it. P is equal to 0, of course, it's junk. As you change the slider, it goes from seemingly impossible to, in some sense, possible. But the goal is, if you know R, and at some level implicitly, if you know P, reconstruct A as accurately as possible. Okay? Obviously, perfect would be great, but something better than obviously all zeros. D is, okay, so in this setup, what we're looking at is that probability P is written as D over N, where the matrix size is like M by N. So we want to control that sparsity, and we want to sit in a regime where D is roughly order 1, which means on average, we're getting D entries per row or column. And so it's like the very sparse regime is where we want to go. If D is equal to order 1, then it's different. Or rather, if D is equal to N, that means P is equal to order 1. But we want to go in the regime where we only take constant on average entries per row or column. Okay, so a common example where this extreme sparsity shows up. So why are we doing extreme sparsity? Because extreme sparsity is a bit more natural of a model in real world applications. So one of the settings that motivated this many years back was this Netflix matrix completion problem where the rows are users, columns are movies. Every time you watch a movie, you rate it. If the number of users or the number of movies is growing, it's not like we're watching at the rate that Netflix is putting out, right? Or at least I'm not. Maybe there's a constant number I watch in a year, maybe 30 at most, right? And but that thing is kind of growing. So we want to be in a regime where we don't want the sparsity to grow with n, because that seems, even if it's nice for theory, it's not quite how these things work, right? So extreme sparsity is challenging, but that's kind of representative of what we're really doing. Here's another fun application. There's a patent you can look up by eHarmony for the same kind of application where on the x-axis, if you would, on the rows of that matrix, it's the users. The columns are things you like. For example, do you like to go camping? Do you like opera? Do you like matrices? You like ramen, and you fill it up, and then it recommends who you might date. I don't know whether eHarmony is still around, but maybe if it works, it shouldn't be around, right? So I don't know. Maybe it's proof that SVD works in some way. Okay, so here's another example where, so same setup, right? You can imagine when you fill up these preferences, you're not really going to fill up. Maybe there might be one or two person who might fill everything up, right? They're like, I'm just going to spend all day ranking everything I want. But typically, you want with relatively few things that you rate to get that recommendation. Here's another example in ChatGPT 2. So in ChatGPT, at the heart of it, it's learning these word embeddings, which means there's a word represented as a string of tokens, if you would. But in this situation, if you think of each word in the dictionary as being represented by one hot, it's transforming it to some embedding of real numbers or real vectors. And the way that embedding matrix is learned at some level is by fitting, it's not that important, but at the heart of that embedding matrix is something called the context window. So it looks at a certain size of the text, sometimes before it, if it's like a causal situation, or acausal is, let's say, different. But essentially, it's looking at the word within a certain window and then trying to predict either the anchor word or what's coming afterwards. So that context matrix is very sparse by design. And the exact sparsity turns out to be that context window, right? So there too, of course, you want to make it big, but in a lot of applications, maybe you might want to understand what happens if it's really sparse, okay? Another setting I'll just mention is in actually training of these things, in pre-training of these neural networks, they often are intentionally making that matrix sparse, right? So they call this, I think, masked autoencoders, where they take the images and they intentionally poke holes in it, and then they try to learn features that are filling in those holes with the idea that somehow masking produces good features. So it's not exactly related to what I'll talk about, but it's intriguing, right? Why does deleting entries give you a better representation than keeping all of it? Yeah, but it's not unrelated to this. So if you've not seen this, of course, the SVD stuff for that matrix completion was celebrated many years ago when people looked at the Netflix problem and then did silly stuff. And then they realized if they plugged in the SVD, it somehow magically did way better than the silly stuff. Of course, now it does even better thanks to other methods, including deep learning. But just to give you a sense of how we can go from the easy to the hard regime, I'll just warm up with a simple example so you can see what makes matrix completion easy, but also what makes it hard, okay? Because we really want to go into the hard regime as quickly as possible. So here's a simple warm up. You know, if I told you that A1, the underlying matrix, was rank 1, and this was the missing entry, then the claim is that that missing entry has to be 2. And the reason, of course, is it's rank 1, so that first column has to be a multiple of the second, and there's really only one way you can go, okay? So extending on that general idea, if I only had one missing entry, it's not a big deal. If I have many missing entries, of course, all kinds of stuff could happen. And the point here is that if I had a matrix which was rank 1, but of this form, so these are so-called localized matrices, as in the entries are not spread out. You have some entries that are big, some are particularly small, like maybe 0. Then one missing entry could mean failure, right? But that's not the situation we're looking at. We want to look at the situation where that A matrix is encoded in such a way that its singular vectors are spread out pretty much uniformly. And that condition is referred to as these singular vectors. They're called incoherent or delocalized, depending on who you talk to. Okay, so here's just a quick slide allowing you to think about what is the easy, less easy, and the really hard regimes for matrix completion. Okay, so we can kind of get a feeling for that just by counting parameters and seeing where do we fit in that spectrum, with the idea that if somehow the number of measurements we have is way more than the number of unknowns, we should somehow be able to solve it regardless of what that method is. So roughly speaking, if I have this matrix which is incoherent with spread out vectors, and it has rank D, or rank R, sorry, then the number of parameters is roughly speaking order of m times r, okay? Ignoring that constant factor. If I observe each element with probability d over n, then roughly speaking, I observe dm entries. So just by looking at those two, you can see that the easy regime corresponds, roughly speaking, to when d is order n. So if d is order n, you have as many, let's just say you have way more number of elements observed, right? If I plug in d is equal to roughly n here, then this n times m is way more than r times m, where r is fixed, and I should be able to solve it, right? That's not too hard. If d is order r log n, and if I plug that in here, you'll notice that r log m becomes like, let's say m log m, and here you have, roughly speaking, m. So you have slightly more equations than unknowns, and you should be able to solve it as well, right? That's typically, and it's not obvious how you do it, but at least you kind of get a feeling that maybe it's not implausible. Where it gets really hard, and maybe fun in that way, is where this d is exactly on the order of r, right? So then, roughly speaking, the number of equations is the same as the number of unknowns, and then something interesting might happen, right? So one might wonder, is it impossible there? How do you do it? What is that method, and so on. Okay, so what I'll focus on initially is a setup which is similar to this easy regime, just to show you how even the easy stuff becomes hard as I change that knob for p, right? So p, in terms of the probability, is regulating the hardness anyway. If p is obviously 0, it's impossible. If p is 1, obviously I know it. Let's see what happens as I change p. with a relatively straightforward heuristic algorithm, if you would, that is the backbone of a lot more rigorous algorithm. Okay, so let me tell you what the algorithm is. The algorithm says if I have a matrix and there are some missing entries, I replace those missing entries with zeros. If I know the rank, I take the truncated SVD of that. So I compute basically the closest rank 4 matrix in this situation, and then I kind of ping pong back and forth. Right? So I fill in the entries that I know, and then so on and so forth. But in this case, let's just think about how we would reason about whether this problem is easy or difficult. If I filled in one entry, if I remove just one entry of this guy, this MIT logo is rank 4. It's a fun exercise if you want to see why it's rank 4. But if I just remove one entry, then you can kind of see that that one entry shouldn't play a big role in the truncated SVD. Right? It's just one entry of this big matrix. Every element of that matrix is roughly 1 over square root of n. So every entry is roughly 1 over n. So the Frobenius norm of this error relative to that one entry coming out is really not too big. Right? So if I take the truncated SVD, I'm already pretty close to the solution. And then hopefully with some hand waving stuff, you can believe that I can fill in the rest. Okay, so with that idea, what happens if I have 70% entries? So in 70% entries, if I replace the missing entries, these black dots with zeros, and then do a rank 4 SVD, what happens? And how do you reason about this algorithm as it progresses through? Okay, so here's an example of what happens. So if I fill in the missing entries with zeros and do a rank 4 SVD, it's not perfect. Right? Actually, it's far from perfect. You see all kinds of artifacts. These banding shows up. But it's containing quite a bit of information that's obviously related to the original rank 4 matrix, and the error is 0.3. Right? So it's not perfect. It's far from perfect. But if I ping pong back and forth using an algorithm that's either nuclear norm based or alternating projection, what you'll see is every time I do the iteration, if I start with this initialization, with every iteration, the error keeps going down. Right? So after one iteration, it's about 0.11. But after 10 iterations, you're almost basically perfect. Okay? So the perspective here is if the first iteration with the SVD by filling in the zeros is pretty good or close enough, or at least not uncorrelated, there's hope, and I should be able to recover eventually by just ping-ponging back and forth. Okay? That's kind of the heart of a lot of ideas. And you can see this in this kind of plot. This is the inner product between the estimated singular vector after a certain number of steps and the true person. So 1 means it's perfect. And it starts off with something not bad, so about 0.3. But then as you iterate, it kind of eventually latches on. Okay, so the point here is, the key insight is that if in step number 1, when I plugged in the stuff with zeros, if I have some correlation, I have hope. If I have no correlation, you might imagine the SVD kind of breaks. Right? So we want to now push the SVD into this very sparse regime where there is no hope, so to speak, and then, of course, redeem it in a different way. Okay, so if I make it sparser and I continue through the iterations, it turns out it's not perfect. You can recover still the MIT shape, but it's really not, it starts getting errors. If I make it even sparser, so like 20% only, now you notice actually the top bands of the the MIT T is sort of disappearing. This is giving you some idea that not all of the rank components can be recovered effectively. Maybe some of them appear or disappear. If I make it even sparser, so like in this case 1%, then it's completely gone. Right? This is a regime where, thanks to the light being off, you can maybe see the important phenomena that actually what shows up is not all 0. Right? It can't all be 0 because the singular vectors have to have norm 1. But the singular vectors, you can see the signature, they look like dots. Right? So the dots represent that what's coming out are actually singular vectors that are very localized. They're actually not spread out. They're kind of concentrating on some points. Okay? And we'll kind of talk about why that's the case and how that's a signature for improving the algorithm. But that's the failure condition where it really is junk. Okay?
That's the first iteration or after?
Yeah, the first, but after that, it doesn't even progress. It's kind of hopeless after this in some way. There really is seemingly no information. Okay, so just to summarize, what happens to the SVD? So this is an example of a matrix that is, I think, 8,000 by 8,000, and it's just a small submatrix. I think it's rank 1 also. If you apply the SVD and do the normalized mean squared error, you get an error of 1, right? Which means it really behaves like it's kind of zero for all practical purposes. Okay, so in this regime, which is really sparse, which is D over N, if D is order log N, that's not a problem. There's a lot of theory from matrix completion with nuclear norms saying that you expect perfect reconstruction. But when it's O1, then you can't expect perfect, you get errors. And SVD breaks down completely. The singular vectors are localized, those are those dots, right? We started expecting delocalized stuff, but it suddenly becomes localized. And this initialization cripples every method that sort of relies on it. So even though this algorithm I described is a bit heuristic, nuclear norm also in this first step is taking the SVD and then it iterates, but it's kind of lost in the water the moment the first step breaks down. Okay, so the point here is seemingly SVD doesn't work, seemingly convex methods don't work because they all inherit this flaw of step one. Okay.
If you values in different ways. Is it clear that the SVD is the limiting factor here, or?
So in this case with SVD, as in this convex thing, the SVD ends up showing up in one way or the other. So for SVD based, step one where you replace with zeros is an issue. There are other methods where you can try to impute. I don't know too much about it, but there's one method I can tell you a little bit about, but not too much about. So there are ways where you try to threshold and take subparts of the matrix and recover that and then impute. But ideally here, what we want to go for is a global method that's not doing anything smart. So I want a very dumb method, like the, without doing too much more. But there are some family of small smart methods that can recover a part of the matrix based on some more information, so to speak. Okay? But I want to talk a little bit about a kind of global dumb method in the sense that it just does it without too much thinking. Okay? Like SVD, you don't have to think too much, right? You just apply it, it comes out. I want something like that. Okay, so I want to give you a little bit of an anchor for how we can reason about this, right? You saw a little bit of a preview. So the key idea, which will give you an idea of how we came up with that method too, because really that chain of thought is kind of fascinating for all kinds of reasons, is that the observed matrix A, right? If I just decompose it in this way, I take the expectation and subtract the expectation, then essentially the expectation is just P times A, right? On an element-wise basis. And this matrix right here, A minus expectation of A, is just what I'm calling a delta matrix. So the delta matrix you can think of as a perturbation. So intuitively, I think you'll believe me if I say that if in some way that perturbation is going towards zero, let's say rescaled by P in some way, but let's ignore that for now, then maybe you feel like the method should succeed, which is sort of the regime where it's perfect reconstruction, right? So somehow, if this largest singular value of that delta matrix is going down, as the size of the matrix is going to infinity, then I expect perfect reconstruction. If it's bounded, then maybe you expect something noisy. And maybe if it's unbounded and blowing up, you expect it to be junk, right? So based on this, maybe intuitively, you have this feeling that when the SVD breaks down, probably the largest singular value of that delta matrix is kind of getting unbounded in a way that just cripples it completely. Okay, so the question at some level is, how do we kind of almost regularize that matrix in some way so that that largest singular value is not blowing up in some way? Okay? And that's where that asymmetric SVD, if you're thinking about it, is kind of coming up. Okay? Question is, what exactly is that asymmetric stuff? So these are a couple of those questions that motivated the talk, which is, in that very sparse regime, is it possible to reconstruct reliably, with a simple algorithm that's not thresholding based? And then what are these limits of reliable reconstruction in that regime? Okay, so let me show you the method that we came up with. There's actually two different methods. In some sense, there's three different methods that two of them are kind of they build on the same construction. The third one is kind of vastly different. But in this setup, you can imagine we had that rank one matrix. The SVD doesn't do anything. And then you apply this so-called asymmetric SVD, and it recovers, not perfectly, but it recovers quite a bit of information. Okay. Turns out there's another matrix called the weighted non-backtracking matrix. I won't talk too much about it. And it does even better. Okay. This one, the complexity of the weighted non-backtracking matrix, it also uses an eigen decomposition, but essentially the amount of compute is order d squared more. So if the sparsity is relatively high, it takes way more to compute. Okay, but these methods clearly kind of recover something in this regime where the SVD sort of fails, but there's still a eigen kind of algorithm hiding inside of it, okay, which is what I want to tell you about. Okay, so here's again that example. One thing that I'll talk about is just the extent to which the distribution of the vectors also matters, but it's not that important right now. Okay, so let me tell you what the idea behind it is and what that asymmetric SVD is, because it's kind of a strange operator in some way. So forgive a little bit the change of notation. This is kind of the same thing, except what we're referring to here is, this is that rank, in this case, N versus R. This is just a low rank matrix, but here what I'm doing is I'm just taking a simpler situation where everything is symmetric without worrying about the situation where, like in the SVD, where the matrix is rectangular. Okay, so in this setup, I'm working with a symmetric matrix, and this is its eigendecomposition. And what I do now is I take this matrix, and in the same way, I multiply it with that masking matrix, except the masking matrix is normalized the same way. So it's like D over N, and it sort of has that the symmetry that symmetric matrices should have. Okay. Now, the important point here is that if I have this matrix A, and if I apply the eigendecomposition to recover its eigenvectors, they too will break down the same way that the SVD does. Okay, so the symmetric problem inherits the same issues as the rectangle, but the idea that we do is we take this A matrix, instead of doing its eigendecomposition, what you do is you form another matrix from it, let's call it like A tilde, where essentially if it's a symmetric matrix, you flip a coin, and if you either take the top part of the, let's say you look at ij and ji, you flip a coin and you either keep ij or ji. Okay, so graphically, this is what we're doing. Imagine that we have this matrix A, which is symmetric. From that, you form a new matrix where you either keep randomly for each element that you observe, the top part or the bottom part. Right, so you intentionally kind of break the symmetry. If I take this matrix and I add it to its transpose, you get back the original matrix, if you would. Right, so I'm just splitting it in this intentional way, and I'm making it intentionally asymmetric. And it turns out this cures everything. So if you do this random asymmetrization, then above an explicit threshold that we can compute using random matrix theory, which depends on the kurtosis of the elements of the eigenvectors, these eigenvectors of that matrix on the right will turn out to be correlated with the original eigenvectors, but the eigenvectors of this one on the left will not be. Okay, so somehow breaking that symmetry reveals structure in a way that having, if you would, more of that symmetry structure doesn't, which is kind of odd, right? It's not obvious, like, at least for me, when I was learning linear algebra, you'd always be scared of going into the non-Hermitian matrices, but here you want to. And the moment you do it, you find structure in a way that you thought wasn't possible to find. Okay, so I'll just show you the nature of the kinds of results that pop up. So yeah, you can find something like a detection threshold, which depends on some parameters. The important thing is, once you find the detection threshold, you can compute even how correlated the eigenvectors are between what you recover and the ones you estimate. And then it turns out this threshold depends on a factor, which I think is kind of interesting. It depends on the kurtosis of the elements of the original eigenvectors, right? So if I give you a matrix that has eigenvectors that are plus or minus 1, the kurtosis will be 1. But if I give you something which is hyperbolic secant, that kurtosis will be 9. So the threshold depends a little bit on how heavy-tailed that matrix is in ways that are not the case for usual random matrix theory. Okay, so that's just what the formulas look like. They're kind of clean for a relatively complicated problem. Okay. So let me show you now what happens in this setup that tells you that the eigenvalues are containing information. So that matrix is asymmetric, which means it has complex eigenvalues. These complex eigenvalues are these dots. In this setup, I have a rank 3 matrix. So in a particular simulation, if I computed the threshold in closed form, that threshold corresponds to the boundary of the circle that's depicted in this dashed yellow line. If the eigenvalues are below under the circle, they don't emerge, and those eigenvectors are basically junk. Okay, so even in this case, some eigenvectors you cannot estimate depending on where they are relative to that spectral radius. If they're contained inside of it, or then they are basically uncorrelated. If they're outside, then they show up and they become real, right? So this is an example of the prediction from the theory of where they're supposed to be. And then what pops out is basically very close to it and turns out to be very concentrated around where you expect. Okay.
After doing your
Asymmetric thing. Yeah. Okay. So in this case, it turns out the degree or the average number of observed entries was 5, and only 1 out of the 3 eigenvectors of the rank 3 matrix could be observed. If I increase the D, so if I make it from D equal to 5 to D equal to 15, you notice that circle shrinks, right? Which you expect in some way. And then now 2 out of the 3 guys pop out. And now you can estimate them, which again makes sense, right? As D increases, you're observing more of the matrix, so more of the eigenvectors should be reliably estimated, and they do pop out of the circular region. Okay, so that's in this case, 2 out of the 3 could be estimated. 1 will not be, just because of whatever eigen SNR it happens to come with. If you increase D even more, at some point, all 3 will come out, right? So one after the other, like an onion, they'll sort of come out. And when we played that movie backwards for the MIT logo, right? Remember, we saw that all 4 rank ones you could see, and then as we lowered sparsity, the top bar of the T sort of disappeared. This is kind of like moving backwards in that simulation. Okay, so as D increases, the circle shrinks, and more of them sort of pop out. Okay, that's kind of the prediction. Here is just a plot showing you how nicely the theoretical stuff fits. So on the left-hand side, this line right here is the theoretical prediction. Because it's a normal distributed eigenvectors, the kurtosis is 3, so the detection threshold is exactly at 3. And then the red line is the prediction from random matrix theory. And then the dots are just, actually the dots in this case are simulation results of the inner product from just one large matrix. So not even averaged. This is like an 8,000 by 8,000 matrix. So you can see the phenomena of concentration, as in the predicted theory exactly almost describes an instantaneous result because the results are concentrated about this red line. Okay. On this plot, you'll notice there's the red line and there's a blue line, which is better. Okay, so you might wonder, where is this blue stuff coming from? Again, we can predict what that performance will be. And here's another weird aspect of that asymmetrization. So this is an asymmetric matrix, so it has left and right eigenvectors. The left and right eigenvectors are not the same, but they're correlated. So it turns out if you average the left and right eigenvectors, you'll do even better because they contain common information and sort of there's an averaging effect in the noise contained in both of them, right? Which is also kind of cool. Normally, again, I've always been scared of the left and right eigenvectors, right? That's not a thing one plays with for non-Hermitian matrices.
Distinct eigenvalues then, right? So that you can pair them appropriately, I guess.
As in when you run the I-guess routine, you'll get the, yeah, the moment you know one, you can also compute the other one out. They come as pairs, right, in that way. The left and the right.
As long as you don't have repeated eigenvalues, that's what I'm saying.
Yeah, at least theoretically, yes. Yeah. But to the extent that it's like a subspace kind of stuff, then you'll still find, I think it inherits the same thing.
These are inner products, yeah, okay.
Okay, so here are those plots showing you that the theory works, averaging does better, and then here is the inner product of the SVD, or in this case, the Eig, if you would, and you can sort of see that it doesn't do well at all, right? And here's an example of the L infinity error, right, instead of inner product error, and you can see the SVD does really badly as you get to the very low sparsity in a way that in the regime where we're trying to get better. Okay, so that's the fun phenomena. This one's a little bit different. So on the left-hand side, all of the simulations are with normally distributed eigenvectors. On the right, on this plot, everything is hyperbolic secant. Again, the theory works. The red lines up with the squares. The blue lines up with the circles. But here you notice the gap between the SVD and the new eigenvectors, if you would, via this method, is greater because the more heavy tail you get, the worse matrix completion gets in that very sparse regime, right? So if you were to simulate this with +1, -1, you wouldn't see much of a gap, but the more heavy tailed it gets, the more you can actually squeeze out of the method in the regime where you might have thought the SVD is hopeless. Okay, so all of that action is just coming from that asymmetrization perspective. And in this case, again, that threshold has moved from 3 to 5, and that 5 has to do with the kurtosis of the elements of that SVD or the eigenvectors. Okay.
In these cases, the matrix is exactly low rank. Is that right?
The latent matrix is exactly low rank, yeah.
And you talked about eigenvectors being hyperparabolic. So you're not talking about the elements of the matrix itself. You're talking about the eigenvectors. I'm a little confused by that. I don't know how to.
So I just think of it as like if the matrix is like theta UU transpose, then the U basically, after I normalize to make sure it's unit variance, it's kind of coming, I look at what distribution that's coming from.
You're generating these planted model.
Yeah, in that way. That's right. So in the way you're thinking, if you had a matrix, then you might think of it as a mixture.
Yeah, okay.
And then it's kurtosis. In general sense, the kurtosis should do it. But here it's really very fine grained. So you really can almost break down every element eigenvector. So technically speaking, just to get very technical on it, is if you had component 1, which was Gaussian, component 2, which was hyperbolic, each of them might have different thresholds based on that, I think, as one goes through it, which is because they really are behaving they induce their own kind of funkiness. Okay, so now maybe you can guess where the asymmetric SVD is coming, right? In some way. So the asymmetric SVD comes from the fact that if I want to compute the SVD of a matrix A, I can compute it from the eigen decomposition of this embedding, which is 0, A transpose, or A Hermitian transpose, A and 0. So I convert the SVD into a symmetric eigen decomposition problem, and then I apply the masking to this symmetric problem, right? So that's where, and then I do an eigen decomposition of it. So it inherits all the nice properties of the phenomena I talked to you earlier, right? So graphically, the process goes like this. If I wanted to do the usual SVD, it's as though I'm doing the matrix, embedding it as like this matrix and its transpose, and then computing its eigen decomposition, and then peeling off the eigenvectors of this matrix to form the singular vectors. But now what I'm going to do is I'm just basically doing that same trick where I flip a coin and either take an element from the top or its reflected part under the diagonal, and then take the eigen decomposition of this matrix, compute its left and right eigenvectors, and then average them or do whatever, right? But that matrix is going to have complex eigenvalues. This matrix is certifiably going to have real eigenvalues, and all of the action comes from this simple procedure. Okay? So one aspect that perhaps you're wondering is, where did this sort of come from, right? What was the chain of thought that led to this unusual construction in some way? That part is sort of, yep.
Before you go on, if you were to state the asymmetric SVD just in terms of the original matrix A, instead of this asymmetric Eig, are you just saying do the regular SVD of a matrix where the entries are randomly?
No, you have to embed it in this. You have to first embed it as a symmetric matrix, and then you have to asymmetrize it. This embedding is important. So this step we often can ignore in usual matrix mathematics just because they're equivalent. The eigenvectors of this matrix are, if the matrix is m by n, the eigenvectors of this matrix are m plus n. So they kind of are contained within that. So we don't need to
express this in terms of a convention.
No. In fact, the weird thing is if you take the SVD of this matrix also, it kind of breaks down. You really do need to take the Eig. Like you could also say what happens if I do the SVD of this matrix, right? Not just the Eig, but that SVD also will break down.
Even if p equals 1, we can't express it because you're still going to do your random thing here and have half above and half below.
Yeah.
Totally different.
Yeah. So it's a little bit, it's a slightly different operation. It's a weird operation, right? It's not, in the p equal to 1, actually, you'll get near perfect in that way. It's not a problem, but it's just weird, right? That how it's containing that information. Okay, so I want to give you a feeling of how to think about it. So in the case where it's perfect reconstruction, we talked about this delta matrix, and I think you can believe what I'm saying, which is if the delta matrix largest singular value is going down to 0, then it just means the perturbation is very small, right? The canonical case was one entry getting shifted. you feel like it shouldn't really change the answer too much. In the case where the SVD is junk, we have the feeling that the largest singular value of this delta is like blowing up. But if somehow I could regularize it in a way that it was bounded, then maybe there's hope of doing it, right? Except I'm not doing the SVD. So the question is, what simulation sort of gave rise to this idea? And it turns out the simulation looks something like this. Okay, so let me go slowly to tell you what's happening. So the dots here again are the eigenvalues of that asymmetric randomized matrix. The lines here are a little bit different. Okay, so the gray lines here represent the singular values, which are all real, but I've just extended them out just so you can see where they fall on the real axis. Okay, and the important point here is in that very sparse regime, you notice the singular values are not really well contained. There's kind of like a heavy tail signature. They're just weirdly flying out. Okay, it turns out you might look at this and say, oh yeah, this is maybe a signature for the largest singular value. But if you pop out the singular vector of this matrix here, they'll be very localized. They kind of break down badly. And the reason they're localized is because it turns out that matrix in that very sparse regime has a few rows that happen to have particularly large number of revealed entries with high probability. So every matrix that's big enough will always have some rows or columns that dominate. And those rows and columns that dominate end up sort of pushing the spectrum out towards infinity. And those singular vectors end up being concentrated exactly on those rows and columns. So the folks, I think Andrea Montanari and a student, I think Siwang Oh, we know from a different context a while back, many years back, unknown to me, they sort of came up with an algorithm where they could prune the matrix by sort of removing those very high, high degree rows and columns and do it. But you got to set a threshold and know where the threshold is, and it becomes, funky in ways that this method, let's say, you don't have to worry about any threshold, right? It's just automatic in that sense. Okay, so the point is these singular values provably turn out to be unbounded. The largest singular value of the delta matrix, if you analyze, turns to exactly infinity. I think it's something like log n or square root of log n, and it goes to infinity. However, that same matrix, if you look at this randomization applied to the delta matrix, it turns out the spectral radius, okay, not the singular value, the spectral radius, which is this circle, is bounded. So the fun fact is the complex eigenvalues have a spectral radius that are bounded. They're all contained in a circle, like a Bode plot, if you know that language. The largest singular value, which is measuring something different, right? The eigenvalues are not the same as singular values here. They go unbounded. So somehow knowing to switch from that singular domain to the eigendomain suddenly opens up this gap that we can take advantage of, and then the rest is just details.
See, bound, are you talking about as n goes to infinity or something?
Yeah.
Okay.
So as n goes to infinity, the largest singular value goes to infinity, so you're in trouble. There's nothing you can do to rectify that, but it turns out for that same phenomena, the largest eigenvalue stays bounded. So then automatically, the moment you know that, you're like, oh yeah, I got to switch my embedding into the complex domain, and then I can squeeze it out. Okay, so that's sort of the thing, which is, it turns out for matrices of that form with that masking matrix, the math insight is that the operator norm is unbounded, but the spectral radius is bounded. And in some sense, the moment you, at least for me, I remember maybe in that paper we kind of wrote this, I think you commented on it, Jeff, was like, we were sort of, my colleague, Charles, he was visiting Ann Arbor like 7 years ago, and I think Literati used to have a coffee shop upstairs. And I remember he told me that he did this with his colleague, and I was like, oh yeah, then this must be true. And we did the simulation having coffee in Literati for a couple of days, and proving it took like 5 years, okay? And a lot of it is really thanks to him and his student, Simone. I kind of learned from them about it, but just knowing that, okay, there's a gap between these two, they're not the same. I hope you can see, right? The moment you see any other problem where there's a gap, you know that you can take advantage of it and switch domains, and you kind of can squeeze information out. I think that's the one fun part about, I think, being folks like us who like math but also like engineering is, in math the object is sacred, so they don't touch it. But for us, it's like, oh, okay, it's a matrix. I'm okay with distorting it if it's going to buy me the signal out, right? For them, the moment it's unbounded, okay, it's unbounded, I'm going to be happy. But the moment we know that another domain sort of, it's bounded, we can switch. We can mess with the data if it buys us information. And That's kind of the stuff here. Okay, so there's another matrix. It turns out it's a little bit different. I'll just show it to you so you can see what it looks like. It's called the weighted non-backtracking matrix. So it's a matrix that's constructed in a very elaborate way. It looks at that matrix completion problem as a weighted graph, and then it enumerates the edges and forms a really big matrix of the size, basically how many edges or connections there are in the matrix by just wiring only very sparse elements in it. And it turns out if you do that, it lowers the threshold by another factor of square root of 2. Okay, so roughly speaking, the idea is the asymmetric construction is throwing away half the information by just splitting it, and this sort of recovers it all the way, except the matrix is much bigger. So it's sort of computationally a bit more infeasible. Here's the same setup where I have a degree or the sparsity of 3, and you notice the very nice complex spectrum that's really nicely bounded in the circle. In this case, one eigenvalue pops out. The second one doesn't because it's inside the circle. If I do this weighted non-backtracking matrix, you get a very nice owl-looking picture, right? But again, you can characterize the circle very nicely. And in this case, that second eigenvalue, which was not revealed in the previous one, jumps out, and you can estimate it. Okay, and there you can see it's slightly better, right? Not significantly, but I mean, we're looking at limits, so the blue line is better even if by not too much. And both of them sort of inherit that same nice property, which is they're better than the SVD, and they're also in this case, better in terms of the L infinity norm, which measures localization in a better sort of way. Yeah, here's just a couple of links if you're curious about the proof. It sort of really boils down to things that Charles and Simon know really well, which is mapping this graph, this matrix problem into a graph problem, really via trees, and then looking at the eigenvectors of trees. They really are great at it, and I've learned more from them about it than I know. But here's just a reference to it. So let me just conclude by talking a bit about what I shared with you, which is this very sparse matrix completion problem, where we look at the regime where the sparsity is order 1, so it's really, really sparse. And we ask the questions, is it possible to reconstruct reliably with error? Right? We don't expect perfect reconstruction, but no thresholding or pruning, unlike these other algorithms that are clever in terms of exploiting that localization structure when it breaks down. It turns out you can with 2 different algorithms. The one I really spoke about was this asymmetric SVD. You can see where that asymmetry is coming in. It's really embedding it into this eigenproblem and then busting it out with randomization and taking advantage of some concentration. And once you do that, it turns out you can solve it and lower the limit of reliable matrix completion below where SVD, nuclear norm, and all of those would typically fail. I'll just conclude with connecting this a little bit to ChatGPT type stuff. In this word embedding, really the fun part is a lot of the matrices are really, really big because the dictionary is huge, and they're really, really sparse. So it's interesting to sort of think, how might we use experiments of this form to understand when that context window breaks down and when we can find information in regimes where you can't quite compute the way they can. Okay, so with that, I'll leave it up for any questions, and I'm curious also what guess you had for asymmetries, the asymmetric procedure that was different than at least what I showed you. Okay, but yeah, I'll just leave it here and open up for questions. What did you think, Clay? What was the asymmetric thing you were wondering?
You meant like a variant of the SVD that was somehow had asymmetry, but
It's not clear what name. It's not a good name, but it's
so yeah, I didn't have any interesting ideas.
the name is not the best. It's not obvious what name, but hopefully asymmetric SVD, someone doesn't just think it's a ChatGPT error, that we meant to say asymmetric SVD was maybe the hope.
So I thought you were actually going to talk about sparse matrices, and so I thought, well, maybe in the normal SVD, both U and V are are dense. They're typically dense orthonormal.
Oh, I see. In that
Maybe
way,
one or the other sparse or some
Okay.
other property, but you're actually really talking about missing data, not sparse data in a way. I mean, it's probably
Yeah.
what people in the field call it, but I really.
Yeah, I
thought
get what you mean.
it's the mass that's sparse.
That's
not the
right.
Data that's sparse.
That's right. It's not. Yeah, the data is not sparse. Yeah, if the data is sparse and you do matrix completion kind of for the other reason is funky. Yep.
Like, what is the gap between, you kept saying we do have error in the reconstruction. So what is the gap there? If there's enough entries, then I should be able to reconstruct with the right subspace, right? So where is the error? Like, we didn't see it in the,
In which one? I'm sorry,
maybe go to the previous slide. So, right, you said, is it possible to reconstruct reliably with error, not perfectly, right?
yeah.
So why can't we reconstruct perfectly if the matrix is exactly low rank and we have enough entries? Where does the noise or the error come in?
Yeah, I don't know, right? I think, that's a good way to say it. I think clearly that the parameter counting doesn't quite do the job for it, right? Because at this limit, the number of observed entries is on the order of number of unknowns. And so clearly there's an inflation factor on top of it that also depends on the kurtosis. I don't know. It would be cool to see how to think about that, right? I think that when they say it's impossible in the CS complexity-like way, they might sort of do I wonder if they do parameter count and say, but I don't know in the statistical way how one would do it.
Like if we have fewer entries than are in a column, let's say, and I give you the subspace, then you still can't complete it, right? Because the fit of like r-1 entries in a vector to a subspace, rank R subspace, it has infinitely many possible fits.
I see. Yeah, I mean, in this regime, the matrix is growing, so you have just a lot of samples of it. You have enough samples to average that part of the error out,
Right.
but not that many that you can overcome it completely.
Yeah, I'd be curious to
Yeah.
look at it with you, just understand the error.
Yeah, yep,
Your theorem page again,
sure.
is
Typically, the theorem looks something like this, which is there is some threshold, which depends on some parameters that are based on the generated model, above which reliable detection is possible. And what is the overlap or the inner product between the estimated eigenvector or the singular vector and the original singular vector? That's kind of the flavor of the theorem. So in this context, it's written in a funky way, but the idea is that there's almost a mapping between the eigenvalues and some number. If it's above this detection threshold, then you can sort of reliably detect it. So in the plots that I showed you, that circle was basically this max of gamma 1, gamma 2, and those turn out to be a little bit complicated, but not too complicated. They depend sort of on the matrix via an auxiliary operator called the variance matrix, where you take that matrix and you square it element-wise, normalize it again, and you look at its spectral radius, and that somehow trickles back up into the detection threshold. So all of that information kind of comes in a funky way.
What is L? How do I interpret L?
L is just the infinity norm of that matrix. It's sort of like what is the largest almost entry, which column, if you would, is as big as it can be, so that there's a feeling of control that it's bounding it, in some way. So in this case, you can kind of see when it's delocalized, each of the entries will be 1 over n, so this L becomes like order 1 in some way. If one of them was, I think the way the theory is derived, it really is almost exact up to a point, so you could put it in the localized regime, but then you'll get a value that doesn't make sense. It'll kind of blow up to n, and you'll say nothing can be recovered, Yep.
So going back to Laura's previous question about the reliable recovery on your near the end. So you're talking about reliable recovery with this method.
With this-
Presumably you could use this method as a better starting point for the iterative POX kind of algorithms or whatever, right? And possibly refine from there.
I imagine so. I've not done that, but yeah. I mean, another one that is fun for me to try would be, what happens, I think, maybe Ching and some of his students or elsewhere have also looked at is like this deep matrix completion, right? In the sparse regime. So there's a question which is also like, okay, this is very hand-tuned, of course, in a lot of ways. What happens if you run a deep neural network to do matrix completion using like the deep matrix factorization that Ching and his colleagues and students have looked at? Like, how far does that go, right? We're using so much information. Yeah, we're using a lot of structure in the low rank explicitly and implicitly. The deep matrix factorization is magical in its own way that you don't do much and still it comes out, right? I think maybe Laura, you might have run those. I think some of your students have also run that simulation. It's interesting to see, okay, how far does that go? And can one go all the way? The other part, of course, in the way, I think when I first did this, I was like, okay, what would Jeff do? Which is the different version of WWJD, but, but I was like, okay, would Jeff convexify it? How would he write this as a convex, but then that's where the eigenvalue thing is funky, right? It doesn't have that Rayleigh quotient-like thing the way for the asymmetric stuff. But that would also be interesting is how would one do an analog of convexification or even as an objective function to indirectly get that? But that would be my putting the Jeff's hat on, which is, I think, useful in this context, right? Like, what would I do if I wanted to make it as a optimization problem where I derived it as a, versus as you might call it, a heuristic?
You have lower bounds. Could you possibly do any better than what you're doing, or is this the limit?
The weighted non-backtracking is lower than the asymmetric one, but I don't know how to, I think that's related to how Laura was asking too, right? I don't know how to, I don't have the technology, or it would be fun to know how does one even talk about where it exactly breaks down. I don't know how to handle the fact that these bounds depend on the kurtosis, and I don't know where that would come in for a universal lower bound, in some way. I think in the information theoretic one, they might just say order of. I don't know if they nail it exactly in that sense either, but yeah, that might be open in that way. Okay.
That norm of Q, where the kurtosis is coming.
Yeah, because you can see, right? It's the operator norm of the squared, so it's sort of becoming the fourth moment, if you would, the moment you square everything up. Okay, anything else? Okay, that's that then. Great, thanks again. I was looking at some of the simulations for this, and I remember doing the proper simulation for this, like, March 20th or something in 2020, which was right when schools and all shut down, right? Maybe you might remember. It was a crazy.
You'll never forget.
Yeah, I was like, okay. I was like, I have 5 hours at night. Let me do it now. I don't have to go in.
So the asymmetric masking, the symmetric masking. Oh, that's really unnatural.